Okay, our last step in our quest for benzene is finding it in the non-aqueous phase liquids or separate phase liquids. So we're talking about something that's like an oil that doesn't dissolve completely in water. It's not completely miscible in water. And we divide these into two general categories for very important reasons. One is LNAPLs, or light non-aqueous phase liquids. They're lighter than water, so they're floaters. They float on the water. And the other is DNAPLs, dense non-aqueous phase liquids that actually sink. So most of the oil you think of floats, but there are some things that sink, and we'll come to that in a little bit here. In the subsurface, the NAPL can be as free product or residual. We just say product means we have some oil stuff like that. With a gasoline spill, we have some actual gasoline there. It's all dirty and gunky a lot of times, but it's gasoline rather than just gasoline compounds like benzene dissolved in water. And we might divide it into free product or residual. So free product is floating there as gasoline or whatever. So it's continuous and it's mobile. It can move around. But after, and I'll scroll down here just a bit here. So the gasoline tank or fuel tank, a lot of the NAPLs we deal with are not gasoline. It drips down there, and as it goes down there, it gets on the water table there, and you have this pool of it there. Well, this moves up and down, and then this stuff, it goes down, but it leaves behind the non-aqueous phase liquid stuck in there between the grains of solids by capillary forces. So that would be residual. So free product is the stuff that's actually moving around there and it's pooling. The stuff left behind and stuck in there is the residual product. The problem with NAPLs is that we actually saw we talked about solubility and dissolution, how 25 gallons can pollute a whole lot of volume of water. So it's sitting there and it can dissolve out. It's not soluble in water. It doesn't dissolve completely in water. We can't just pump water and get it out of there. But it's also contaminates the water. If it wasn't soluble at all, the water wouldn't get contaminated. So that's the issue of it. So with LNAPLs, they float on the water table there. And you have, we mentioned this early in the class, capillary fringe. And so it's kind of floating there, and it goes up and down, and you get a smear zone. It volatilizes from that, the gaseous phase, the vapor pressure from the gasoline. We're focusing on the benzene coming out of the water through Henry's law, and then it dissolves in the water. So that's an LNAPL. LNAPLs are like fuels, gasoline. These are the specific gravities. 0.7 diesel oil, crude oil, fuel oil, kerosene. And as I mentioned, it's in the ground there, it gets weathered. The most volatile stuff kind of goes away, not completely. We deal with some sites that are 150 years old, and there's still some volatile chemicals in there. And it accumulates dirt, so it looks all gunky and stuff a lot of times. Sometimes you can pump it out, fresh gasoline spill, and you got to send it somewhere to get taken care of, but it can actually be reused. So those are the fuels. In those fuels, some of the things we're concerned about are the BTEX chemicals. We've mentioned benzene a lot. We said it's 0.5 to 2% of gasoline. Benzene, toluene, ethylbenzene, and xylene. Those are the BTEX chemicals. Benzene is a ring, 6 C's, 6 H's. Toluene, we take one of those H's off and we put a methyl group on there, a CH2. Ethylbenzene, we put an ethyl group on there, 2 C's. And then xylene, we have 2 methyl groups on there. So there's actually 3 different isomers of xylene, whether they're next to each other or across from each other. And I didn't draw all that in there, so we're not going to go into that. So those are when I say BTEX, that's what we're talking about, those chemicals. And those frequently come up as chemicals of concern or constituents of concern, contaminants of concern in LNAPL sites. And as I mentioned, they float and smear on the top of the water table. So for any NAPL, you need to remove the source to begin with. Otherwise, it's going to be a long-term source, just dissolving out forever and ever. A couple technologies that can work with that. If you have volatile chemicals like gasoline, you spill it on the on the parking lot, it goes away pretty fast. So soil vapor extraction, where you pull air through the subsurface to get the gasoline out, that works. And air sparging, you inject air into the water table, which does two things. It helps the volatilization and also increases the oxygen for biodegradation. So LNAPLs are mostly fuels and stuff that floats on the water. DNAPLs. DNAPLs are a big problem. In my graduate school work many years ago was mostly about DNAPLs. There are research projects. And for EPA, I worked on the DNAPL site assessment survey, where kind of after a lot had been done in Superfund, they said, we're finding DNAPLs are a big problem. Let's go review old previous sites to see if they had DNAPLs there. So I looked through the records there. So the DNAPLs head down. If you have a fuel spill, and I'll get ahead of things here. Chlorinated solvents is usually what we're talking about. PCE, which is also tetrachloroethylene, that's dry cleaner fluid. TCE is a degreaser. Methylene chloride and carbon tetrachloride are the chlorinated solvents that are used a lot. So you have a storage tank of those that leaks out. It hits the water table and then it just keeps going because it sinks. It's a sinker. It's more dense than water. These are 1.3 to 1.6 specific gravity. And then it can hit the bottom layer, and if there are fractures in there or some other way to get through it, you can keep going that. One of the sites I reviewed with EPA under the DNAPL site assessment survey, I never went to the site, but I went through their records. It was a chemical waste dump that was this pond that was between, it was a ways from, but between two drinking water reservoirs. And the attraction of that for a chemical waste dump is that you back your truck up and you dump all the liquid waste there, and then it's gone the next morning because it had like fractured rock under it. So I don't know whatever happened with that one, but that kind of scared me a little bit. So this DNAPL heads down in there, and it's really hard to get out of there. Might be hard to find it down there to begin with. The DNAPL are chlorinated solvents, as I mentioned. PCE and TCE in our research in grad school, that's mostly what we looked at. Here, by the way, I stuck a photo in here of new and old transformer oil. So you can see how it's clear to begin with, or light, and then gets darker. PCBs, polychlorinated biphenyls, are transformer oils. So PCBs is another common thing. These are, I say mobile, not viscous, so they're liquids that move around pretty good. PCBs are gunky stuff. It's not really liquid. It's not tar, but it's kind of tar-like stuff that's stuck in the ground there. It's polychlorinated biphenyls. We're not going to go through the organic chemistry of it, but a benzene ring, when it's stuck to something else, we call that a phenyl. And then if we started putting chlorines on there, we have more than one, we get a polychlorinated biphenyl. And there's lots of different combinations of where we can put those chlorines. So there's a whole bunch of isomers of those. So that's why they're always plural, PCBs. There's different isomers of their different. So it's this gunky stuff. Polyaromatic hydrocarbons. That's what I deal with a lot these days. Those come from wood preservatives, creosote coal tars. So in Pennsylvania here, we have a lot of old manufactured gas plants where they got oil and then they boil it and they made gas before natural gas got used a lot. And the waste and pollution from that, you get a lot of polyaromatic hydrocarbons. This gunky stuff. Found wood preservatives. I don't know if they still do. When I was a kid, we'd go find telephone poles and we look at the gunk on them. They put this gunk on them as a wood preservative. That was a creosote that was filled with polyaromatic hydrocarbons. When I was with EPA again, I went through some sites of old wood treating operations from 100 years ago. They had a lot of these. These aren't really in NAPL form. There's this gunk that's stuck down there, but we still call it products because it's an oil. It's not all dissolved in water. It's not moving around very much. I don't know if that's right to say rarely mobile in NAPL form. So it is in NAPL form, but it's not mobile in NAPL form. couple of these, naphthalene, solid mothballs. That's one. Anthracene, it's a component of coal tar. So a benzene is an aromatic ring. We start sticking those rings in there together like that. If they're connected here with across their carbons, those are phenols. If we connect them like one side of it there, then that becomes a polyaromatic hydrocarbon. So the DNAPLs are difficult to find and difficult to clean up. So if there is NAPL there, LNAPL or DNAPL at your site, that's a big source of the chemical mass. So I mentioned these examples we did before, where 25 gallons of gasoline, even though it's only 1% benzene, you get a kilogram and half of benzene out of that. That's dissolving out at 10 milligrams per liter. It's going to take 37,000 gallons to dissolve that out. And that's an underestimate because you don't really have, if you move the water, it takes time. You don't really have equilibrium conditions. A little note here, something we did in the DNAPL site assessment survey. If soil concentrations are real high, is that adsorbed chemical or is there a residual product in the soil? So we take soil borings, we send the soil samples off to a lab, we get back the results. And it tells us the concentration of chemical on the soil. So in the previous section, we went through sorption, we said concentration of chemical on the soil is Kd times the concentration of water, where Kd can be calculated as KOC times FOC. Well, if we have a concentration, if we take 40 milligrams per liter, I just took a real high number here, we can say that that's the maximum the water concentration will be. So if we have an accurate estimate of the organic carbon on a soil, we can know what the maximum adsorbed concentration would be. So if our lab comes back and our concentration on the soil is much higher than that, it's probably not just stuck, adsorbed to the soil. It's probably got some drops of residual in there, some little smears of residual in there. So I'm just showing that here. If, depending on the organic content in the soil, if we get a concentration that's higher than expected from our adsorption, we have some free product there. This is where I got that 40 number from. We said usually we did before, we said 10 to 20 is pretty typical, but just for a max, I'll take 40 up there. So we're about to calculate the mass of the chemical in the NAPL. I just wanted to remind us first, the chemical dissolves from the NAPL into the water at its solubility, but its solubility is not the full solubility of, for example, benzene, 1770 milligrams per liter, 1800 milligrams per liter. It's the fraction of benzene in the NAPL times the solubility of benzene. The mass of chemical in the NAPL, we're going to go directly in the NAPL. We just take the volume of NAPL, then we take it times the density, which is the mass per volume, times the mass fraction of the chemical. For example, if I have 95 liters of gasoline with a density of 0.74 kilograms per liter, this is an LNAPL, it's floating on the water, and it says it takes 2% benzene without worrying about whether that's a mass fraction or a whatever. If we take 95 liters times 0.74 kilograms per liter times 0.02, we have 1.4 kilograms of benzene. So that's actually what we did a couple lectures ago in our example there. So let's do it for our where's the benzene problem. The volume of the NAPL is very similar to what we did for air and for water. So we have the total volume, which is, again, 1,000 cubic meters, times the porosity, 0.35. We've had that before. That's the 350 cubic meter pore volume. That times the saturation, which the NAPL saturation is 0.02. So 2% of that 350 is NAPL equals 7 cubic meters. So the mass of the NAPL then is the 7 cubic meters times the density of the NAPL, which I have up here, specific gravity 0.75, which is the same thing as saying 0.75 kilograms per liter, times 0.75 kilograms per liter, the cubic meters, and we have liters there, so times 1,000 liters per cubic meter is 5,250 kilograms. All right, that seems like a lot. Well, with 350 cubic meters, 2% of it, that makes sense. So the mass of benzene in the NAPL then is the mass of NAPL, 5250 kilograms, times the mass or weight fraction of benzene in the NAPL, which is up here 0.8%. So it's be 0.008, and that equals 42 kilograms. So we had 42 kilograms in the NAPL. We compare that to, we had 8.4, didn't even keep any more digits than that, 8.4 kilograms on the soil, 0.1, and I'll keep one more digit for that, 3 kilograms in the air, and then 3.5 kilograms in the water. So the air is the smallest one by far, but it actually turns out for a lot of NAPLs, that is the big concern, is that chemical moving in the air, and then also it helps us for remediation to get rid of that air. So the total NAPL in our contaminated zone here, if I add those up, is right about 54 kilograms, which the NAPL was 42 kilograms, so that's like 78% of that. So most of our benzene was in the NAPL. So the answer to where is the benzene? Well, it's all over in these different phases, but a big part of it is the NAPL. So we need to get rid of that. We need to get that out of our source area to clean up the site. All right, so we've quantified our NAPL here. The next thing I'll do is I'll walk you through real quick a homework assignment where we repeat this.